Hello class, welcome to the Stat 215 Lecture 5 video. In this video we have 5 objectives. First, we would like to understand the concept of a random variable. 2, we would like to distinguish between discrete and continuous random variables. Third, we'd like to find the probability distribution of a discrete random variable. 4, we're going to find the cumulative distribution function of a discrete random variable. And 5, we're going to create a probability histogram. Let's get started with our first objective, understanding the concept of a random variable. So to start off, what is a random variable? Well, an informal definition of a random variable is a variable whose values depend on the outcomes of a random phenomenon. If you don't remember what a random phenomenon is, go back and check your earlier lectures. A more formal definition is a function that associates a real number with each element in our sample space. Let's take a look at an example. So let's consider the testing of 3 electronic components. Let D denote a defective and N denote a non-defective electronic component. Then our sample space will be non-defective, 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 defective, non-defective, defective, non-defective, non-defective, defective, 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 non-defective, non-defective, defective, non-defective, defective, 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 non-defective, defective, defective, defective. In other words, it's all of our possible combinations of pulling 3 electronic components and all possible permutations of things being, or rather combinations, not permutations, of defective and non-defective components. So let us suppose that we are interested in the number of defective components. Each point in our sample space will be assigned a numerical value of 0, 1, 2, or 3, which is going to be the number of defective components in each of our possible outcomes. And we let these values be assumed by a random variable x. So continuing our concept of a random variable, we usually denote our random variables with a capital letter. Again, usually this is going to be a capital X. Lowercase x is a value of the random variable, capital X. Each possible value of capital X represents an event that is a subset of the sample space for the given experiment. So using our previous example, if we let capital X equals 2, that corresponds to event A, where we have are outcomes that have 2 defective components, meaning DDN, DND, and NDD. Let's look at another example. Suppose we have 2 balls are randomly drawn in succession without replacement, and highlight that, from an urn containing 4 red balls and 3 black balls. We are going to let y equal our number of red balls. We can agree that our sample space will be 2 red balls, a red then a black then a red, or 2 black balls. Again, since y equals our number of red balls, we have the options of y being equal to 0, meaning the situation where we pull 2 black balls, y equal to 1, which corresponds to our red then black, or our black then red, and y2 corresponds to when we pull 2 red balls. Let's do another example. Let us say we roll a die until a 5 comes face up. So let f equal 5 and n be any other number. Our sample space in this case is going to be a bit different than the others, because we're going to have to keep rolling until that 5 occurs. So if we get a roll on the first, if we get a 5 on the first roll, then our outcome is simply F. If it happens on the second one, that means first we rolled a non-5, then a 5. Then our next one could be 2 non-5s, then a 5, or 3 non-5s, then a 5, and then it keeps going. As you can see, or think about, this sample space is possibly infinite. Well, it's not possibly infinite. It is infinite. Unlikely to actually be in practice infinite, but theoretically infinite. But it is also countable. So we let x equal the number of rolls until a 5 occurs. And it would take on the values of 1, 2, 3, all the way until infinity, theoretically. Notice that we don't have the option of a 0 in this case because in order to get a 5, you must have at least 1 roll. This brings us to our second objective, to distinguish between a discrete and a continuous random variable. So a discrete random variable is a set of possible outcomes that are countable. A continuous random variable can take on values on a continuous scale. This is usually measure data such as height, weight, temperature, distance, or life periods. So one example would be if we let x be the random variable defined by a waiting time in hours between successive speeders spotted by a radar unit. X can be any value such that x is greater than or equal to 0. In this case, x is a continuous random variable because we're measuring an infinite amount of time that may occur or may never occur. We could be waiting for an infinite amount of time. And it's not something we can count in like a whole number because think about of like a fraction of a second. So finally, let's take a look at objective 3. Find the probability distribution of a discrete random variable. So a discrete random variable assumes each of its values with a certain probability. For example, if we flip a coin 3 times and we let x equal the number of heads, our possible values of x and our probabilities are shown as follows. So with 3 flips of a coin, we're either going to have 0 heads, 1 head, 2 head, or 3 heads. Below, we have our different probabilities. Now, you can either think this through, or if you need to, you can write out your sample space. Since it doesn't take too long, let's do that now. So, we either have the situation where we are going to have 3 tails, 1 head, so head, tails, 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 head, tails, or tails, tails, head. The situation where we have 2 heads, 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 tails, heads, tails, heads, or tails, heads, heads, and finally one situation with 3 heads. So our sample space has 8 outcomes, and we can see, change the color here, there is 1 out of 8 chance of there being 0 heads, 1 out of 8 possibilities to have 3 heads, and 3 out of 8 to have 1 and 2 heads, respectively. So, in order to do a probability mass function, we may use a formula to represent all of our probabilities of our random variable x. We'll show this as f of x equals the probability of x equals x. The set of our ordered pairs, x comma f of x, remember you can think of f of x as y, our response, and is our probability mass function, also abbreviated as PMF, of discrete random variable x if for each possible outcome x. A couple little things we need to know. F of x must be greater than or equal to 0. The summation over x of f of x must be equal to 1. And our probability of x equals f of x. Let's continue this with an example. So a shipment of 20 similar laptop computers to a retail outlet contains 3 that are defective. if a school makes a random purchase of 2 of these computers, what is the probability distribution for the number of defectives? We will let x equal the number of defectives. Well, for us at this point, we understand that we have a possible value of 0, 1, and 2. Okay, so the first thing we want to know is how many ways to purchase 2 laptops from our 20. Now we know that there is no order to this, so we are thinking of a combination. So in this case, we are going to do 20 choose 2. Using our formula, that is going to be equal to 20 factorial over 2 factorial multiplied by 20 minus 2 factorial. This is going to be equivalent to 20 factorial over 2 factorial multiplied by 18 factorial. Simplifying, this is going to give us 20 times 19 times 18 factorial over 2 factorial times 18 factorial. I'm going to simplify. I know 2 factorial is just 2 times 1, so I'm going to leave this as 20 times 19 over 2, which is going to give us 190 ways. That's quite a lot when you think about it. Next part of this is we want to know how many ways to purchase 2 working and 0 defective laptops from the 20. So, there were, in our 20, 3 defective. So, that would be 3 choose 0, because, again, of the 3 defective, we select 0 of them. And then it's going to be 17 choose 2. Now I want you to think about this. Notice the top of our functions. We have 3 plus 17. That is our total laptops. This represents the non-working. This is the working. Or excuse me, defective. So 3 choose 0 of the non-defective multiplied by 17 choose 2 of the defective. This is an application of our multiplication rule. So 3 choose 0 is 1 multiplied by 17 factorial over 2 factorial multiplied by 15 factorial, which will equal 17 times 16 over 2, which will give us 136 ways. So, again, how many ways to purchase 2 working and 0 defective laptops from the 20? There are 136 ways. Woo! Let's do this again. So, now, how many ways to purchase 1 working and 1 defective laptop from the 20? So again, we have, of our 20, 3 defective, 17 non-defective. We want to choose 1 defective and 1 non-defective. Using our multiplication rules, this is going to be 3 multiplied by 17 factorial over 1 factorial multiplied by 16 factorial. This will equal 3 times 17, or 51 ways to purchase 1 working and 1 defective laptop from our 20. This makes sense. There are more working laptops than defective laptops, so we should have more ways for getting 2 working as opposed to having 1 defective. Now, if we do this next question right, we should have even less ways, because how many ways to purchase 0 working and 2 defective laptops from the 20? If you recall, we have three defective laptops and 17 working. We are assuming of the 3, we choose 2 that are defective, and of the 17 working, we select 0 of those. Using our skills, this is going to be 3 factorial over 2 factorial multiplied by 1 factorial multiplied by 1. Remember, anything that's n choose 0 is going to equal 1. So this is simply going to equal 3 times 1, which equals 3. So there are only 3 ways to purchase 0 working and 2 defective laptops from R20. Now that we have done all of this, we can actually make our probability mass function of x. Exciting, right? So, starting off from our first question of how many ways to purchase 2 laptops, we had 190 ways. That's going to be our denominator in our probability mass function. 190. Now we have our 3 situations where we had our 0 defective, which was 136, our 1 defective, which is 51, and last but not least, 2 defective, which is 3. This should be correct. One way to double check ourselves is these fractions should add up to equal 1. Let's check this now. So 136 plus 51 equals 187 plus 3, 190. Perfect. That means we did everything correct. Another way to have done this was to create a formula. The formula in this case would be f of x equals 190 multiplied by 3 choose x multiplied by 17 2 minus x. So think about this. Every time we did this, we had our 3 and our 17, our 3 defective, our 17 working. We were selecting 2 laptops. If we let our first choose be some value x, then that means our second choice for our working laptops had to be 2 minus x. That would give us our values of ways of working, or rather situations of how many ways of our purchasing. To turn that into its probability, we needed to have it over our number of ways in our sample space, which would be 190. So together we have created this formula. Let's move on to the next slide, or should I say, the next objective. We want to find the cumulative distribution function of a discrete random variable. You'll notice in this lecture we've been focusing on discrete random variables. That's because another lecture will focus on the continuous random variables. So let's start off by defining the cumulative distribution function. The cumulative distribution function, also abbreviated as CDF, is written as capital F of x of a discrete random variable x with PMF f of x. And it is capital F of x equals probability of x being less than or equal to x equals the summation of t less than or equal to x of f of t for negative infinity less than x less than infinity. Let's look at our example. So for our coin flip, which we did 3 times, we let x equal our number of heads. And if you remember for the probability, we had a 1/8 probability of having 0 heads, a 3/8 of having 1 head, 3/8 probability of having 2 heads, and a 1/8 probability of having 3 heads. the CDF of x is our capital F of x equals 0 for x being less than 0. Remember, we have to have at least, don't have the option, of having less than 0 heads. That's not possible. Your cumulative distribution functions are almost always going to start with 0. Next, from 0 to 1, our probability is going to be 1/8. For 1 less than or equal to 2 less than 2, it's going to be 1/2. You may be wondering where this value came from. It's a simple addition. This is for f of 0 plus nothing. Whoops, haha. Getting ahead of myself. This is for f of 0. Our next one is for f of 0 plus our f of 1, meaning the 1/8 plus 3/8 equals 4/8. For our next one, it is f of 0 plus f of 1 plus f of 2, which equals 7/8. And then finally, it is 1 for x greater than or equal to 3. And in that case, we add up all of our probabilities, and if we have our sample space, we're adding all our probabilities, it should be equal to 1. Let's take a look at another example to try to make this a little clearer. So, if a car dealership sells 50% of its inventory of a certain car equipped with side airbags, find the PMF for the number of cars with side airbags among the next 4 cars sold. So, first thing we need to think about is how many elements are in our sample space. Okay, so we have 2 ways to sell our first car, airbag or no airbag. Equally, there are 2 ways for our second, 2 ways for our third, and 2 ways for our fourth. So this means the number of elements is going to be 2 to the 4th, or 16 ways. So there are 16 elements in our sample space. Again, how did I get that? There are 2 ways for our first car, 2 ways for our second car, 2 ways for our third car, and 2 ways for our fourth car, or 2 times 2 times 2 times 2, or 2 to the 4th. Let's continue with our example. So since the probability of selling a car with side airbags is 0.5 or 50%, all of the elements in the sample space are equally likely to occur. We let x equal the number of cars sold with side airbags. So we're going to have x take on our values of 0, 1, 2, 3, or 4. Remember, 0 will be the case where the car has 0 number of cars sold with an airbags, and 4 is the number of cars sold with side airbags. Hope that made sense. So continuing our example, how many elements in the sample space correspond to x equals 0? Then we are asked to find the probability of x equals 0. Again, x equals 0 means 0 out of the 4 cars have a side airbag. Now, so that means of our 4 cars, 0 had the airbag. There is only one way for that to occur. Now to find our probability, we know that there are in our sample space, there are 16 elements, so our probability is going to have to be 16, or out of 16. And using our choosing, it is going to be 4 choose X, which in this case is going to be 4 choose 0, or 1/16. I'm going to put a star at the top to show our formula that I just developed. We are going to let the probability of X equal to X, again, this should be a capital X, equal 1 over our sample space multiplied by 4, our number of cars, and X. Of those 4 cars, how many of them have side airbags? Let's move on. How many elements in the sample space correspond to X equal to 1? And then we are also asked to find the probability of X equals 1. Meaning we sell 1 car with side airbags and 3 cars without. Okay, so once again, 4 cars, 1 with a side airbag. So we are doing 4 choose 1, which is going to equal 4. Meaning our probability of X equals 1 is going to be 1/16. 4 choose 1, or 4/16. Not too bad. Let's keep going. Next we are asked how many elements in the sample space correspond to X equals 3, X equals 2, and X equals 4. And then we are asked to specify our PMF for X. I've already done the last part, but we'll do it again anyways. So for X equals 2, we know it's going to be 4 choose 2, which would be 4 factorial over 2 factorial multiplied by 2 factorial, which will equal 6. Meaning our probability of X equals 2 will be 1/16 multiplied by 4 choose 2, or 6/16. Let's do this for X equals 3. This will be 4 choose 3, 4 factorial over 3 factorial multiplied by 1 factorial, which is going to equal 4. Therefore, the probability of X equals 3 will be 1/16 multiplied by 4 choose 3, which will equal 4/16. Last but not least, 4 choose 4. This will be 4 factorial over 4 factorial multiplied by 1 factorial, which is going to equal 1. Our probability function will be the probability of X equals 4, 1/16 over 4 choose 4, which will equal 1/16. From here we can write out our PMF. F of X equals the probability of X equals X, which equals 1/16 multiplied by 4 choose X, for X equal to 0, 1, 2, 3, 4. Woo! That took a little while. Let's keep going and look at our objective 5. Creating a probability histogram. So a graphical representation of a probability distribution, we can use our histogram. So if we take a look of our airbags examples, there was 1/16 probability for there being 0 and 4 cars. There was a 4/16 for 1 and 3 airbags of our cars selected, and a 6/16 when we have 2 cars, or X equals 2. Again, this is just a nice visual way to draw ourselves a histogram. But I realize as part of our CDF, we never are part of that CDF function section, we never actually found the CDF for X. So let's do that now. capital F of x is going to equal large curly bracket. We start at 0 for when x is less than 0. Now we're going to go from 0 is less than or equal to x is less than 1. This is the situation. So I'll write side note for when we have f of 0. If we look up, we remember f of 0 is 1/16. For that cumulative distribution, remember that means we are going to add. So for our next one, from 1 less than or equal to x less than 2, this is f of 0 plus f of 1. Scrolling up, that means we're going to add 1/16 plus 4/16, which is going to give us 5/16. Now for the next one, for 2 less than or equal to x less than 3, this is f of 0 plus f of 1 plus f of 2. Scrolling up using our histogram, 1/16 plus 4/16 is 5/16 plus 6/16, which is going to equal 11/16. Let's keep going. We now have from 3 less than or equal to x less than 4. It's going to be, f of 0 plus f of 1 plus f of 2 plus f of 3. So 1/16 plus 4/16 plus 6/16 plus 4/16. That is going to equal 15/16. Now last but not least, we are going to have x greater than or equal to 4. And for this, it's going to be f of 0 plus f of 1 plus f of 2 all the way to f of 4. And if we add up our whole distribution, it should equal 16 out of 16 or 1. Hopefully that is not too bad and you remember how to add your fractions up. Let's take a look at a graph of our discrete CDF. So using our airbags examples, from 0 to 1, our probability is at that 1/16. The second we are actually including 1, that it was the 1 is less than or equal to x, we jump up to that 5/16. Once we hit that less than or equal to x, we jumped up to 11/16. Jump again, 15/16, and then finally we are at 1. For our cumulative distribution functions, we should start at 0, end at 1. Okay, so that brings us to the end of Lecture 5. I know a lot of this was probably very new to you, so again, I encourage you to email and ask me questions, and re-watch the video if you need to, and don't forget to read your textbook. So a summary of what we've done so far in this lecture: we now can define a random variable to associate a real number with each element in the sample space. 2, we can now define a probability mass function for a discrete random variable x to specify the probability of any given value x. And we've learned about the cumulative distribution function, and we specified it as the probability of x less than or equal to x. Okay, one more time. Have a great night, everyone. Don't forget to do your homework.